Hello everyone, I'm Devon from the Chinese University of Hong Kong, and today I would like to share with you our research on learning and testing Markov chains using a combinatorial notion which we call the kcover time. This is a joint work with Professor Siuon and Singhei, both from the Chinese University of Hong Kong. So let's begin. In learning theory, there is a fundamental question of how many samples do we need to learn and test discrete distributions. So for example, if we have a black box of colored balls, and then we draw some samples, RID, from this black box. So we have like x1 up to xn denoting the color of these n balls. And then we would like to ask, what can we infer? What do we know about distribution of the colored balls in the box? So one problem we might ask is, what is the distribution of colored balls in the box? This is called the learning problem, and we can also ask how close is the distribution of colored balls is to some reference distribution that is priorly known, which we call the identity testing problem. And there's also other problems, like what if we have two black boxes and we draw sample x1 up to xn from black box A and another sample y1 up to yn from black box B. And using these samples, we would like to ask how similar are the distribution of colored balls in these two boxes. This is known as the closeness testing problem. For these problems in the setting of discrete distributions in RID samples, tight up to constant factor sample complexity bounds are known. So we would like to ask some similar problems in the setting of finite state Markov chains. So it's kind of different because we don't have RID samples here. The samples are kind of correlated. And many questions just naturally carries over in this setting. What is the sample complexity of learning and testing Markov chains? And now we would like to introduce the notion of kcover time using an example of learning Markov chains. So we assume we have sample x1 up to xn from an irreducible Markov chain. By irreducible, we mean that the transition diagram of the Markov chain is strongly connected, and we assume this Markov chain has m states. And the transition matrix is represented by the entries. Mij is the probability of transitioning from state I to state j. So from this Markov chain, we can draw a sample x1 up to xn, and then we have a learner A that takes these samples and outputs a transition diagram m hat. So this is a kind of what's your guess for the transition matrix M? And we measure the error as the following distance matrix. So it is in fact the infinity matrix norm between M and M hat. A very important observation is that, in fact, this distance matrix can be expressed as the maximum over the total variation distance between the conditional distribution from state I to the conditional distribution from state I that you guess, okay, which we denote as p hat. And this DTV is just the total variation distance that is widely used in the literature of learning and testing discrete distributions. And this expression naturally suggests a two-stage learner for Markov chains. So in the first stage, the learner just gets enough samples so that it has sufficient transition pairs from each state. So it has enough samples that transitioning from state 1 to another state, from state I to another state, and up to state M to another state. And now, by the Markov property, when we focus on the transitioning pairs from state I, we can just treat them as RID samples from the distribution P dot I. Okay, just a conditional distribution from state I. And then we can invoke another discrete distribution learner, A prime, in stage 2 to get the conditional distribution from each state I, and then compose this P hat to get our M hat. So for stage 2, many is known because it's just a ID learner. But for stage 1, we still have another question, like how many samples is enough? In some scenarios, it is known. So for learning ergodic chains, so by ergodic, we always mean uniformly ergodic in the literature. So for learning these ergodic chains or closeness testing ergodic chains, Wolfer and Kontorovich has shown that these many samples is enough. However, we would like to say something more, like have it like more general upper bound for learning, testing problems involving a broader family of chains instead of ergodic ones, like irreducible ones. So an important observation is that, in fact, to learn a Markov chain, it suffices to cover the state space k times. And what is this k? This k is just the number required by the RID learner A prime, right? So it naturally motivates our definition of kcover time. So the kcover time is just a combinatorial quantity that is defined as the expected time to cover the state space k times. And we assume arbitrary starting point, or you can say a worst case starting point. And now we have defined the kcover time, and then the core task is how can we bound this kcover time. So for ergodic chains, in fact, we can derive the following bound on the kcover time. So for an uniformly ergodic Markov chain with minimum stationary distribution pi star and a pseudo-spectral gap gamma ps, we can bound this kcover time as the following. So we remark that for finite Markov chains, ergodic is essentially equivalent to irreducible and aperiodic. So ergodic chains also doesn't cover all chains that are irreducible and reversible. So we still need something more for reversible chains. So here's what we have proven. So for irreducible and reversible chains, we can also bound the kcover time as the cover time plus k over the minimum stationary distribution. And this bound is tied up to constant factors. Also, for general irreducible chains, we can also derive an upper bound on and lower bound on kcover time up to logarithmic factors. Is essentially also the same as previous one, just cover time plus k over the minimum stationary distribution. And we remark that it is because we are able to derive bounds on kcover time that enables us to generalize all those learning and testing results for ergodic chains to general irreducible chains. And we remark that for irreducible chains on finite states, cover time is finite and pi star is strictly positive. So for any finite k, the kcover time is also finite. Our bound, yeah. And so what are the proofs? So there's a simple lower bound for the kcover time. So just we need to cover the state space at least once using the cover time. And then we need also to visit the hardest to visit point k times, which takes about k over pi star times. And combine them, you get a lower bound, which is kind of trivial. So for the upper bound, which is some kind of non-trivial part, is that for ergodic chains, we can use the concentration inequalities by Pauling, and then use some union bound, which introduces logarithm factors in the upper bound. And for reversible chains, we are able to do something better to shave off the logarithmic factors. So we can in fact use the generalized second Raynight isomorphism theorem and plus some concentration results for Gaussian processes to remove the log factors. And for irreducible chains, we are also able to bound it by exponential decay of the k-hidden time of Markov chains and plus union bound, which also introduces logarithmic factors. And as a natural application of our bounds, we are able to epsilon learn irreducible Markov chains using these many samples. So what is the learner? The learner is just we just get kcover time number of samples and then invoke the IID learner for each state. And we are also able to closeness testing irreducible chains using these many samples. And what is the closeness tester? Again, it's just simply get kcover time number of samples from each chain because there are two chains. And now we can invoke IID tester for each state. And identity testing as well. We just get kcover time number of samples and then invoke the IID tester. So in fact, our notion of kcover time also simply applies to many other learning and testing problems like tolerant, closeness testing, tolerant, identity testing, and so on. And it also applies to a broader family of chains like irreducible chains or reversible chains instead of only ergodic ones. And we also like to remark that our notion of kcover time is of independent interest itself as a combinatorial quantity, and it might be useful for analyzing other algorithms involving Markov chains as well. And after all, we still have some interesting problems that we just cannot solve for now. So, for example, can we remove the log factors in the kcover time upper bound for irreducible chains so that we also have the lower bound tied up to constant factor for irreducible chains? A possible way we are trying is to use the isomorphism theorems for irreducible chains that generalizes those for reversible chains. And since this isomorphism theorem involves some process, prominental process that is less known, less studied, so we need even to prove existence and concentration results for these prominental processes related to irreducible chains as well. And another important question is, can we also prove tight lower bounds involving learning and testing Markov chain problems using a unifying idea as well? So that's also an interesting question we would like to answer. And that's all for my talk. Thank you for listening. Thank you.